molecular aldol reaction. Okay, because it's happening between two different molecules. Now, can it be done for intra-molecular aldol condensation reaction? Let's see. I've given you something like that over here. I'm taking very simple molecules, okay? We get more complex as we go on. Again, is it alpha beta? Oh yes. So you can apply aldol condensation reaction over here. That is the first thing you have to keep in mind. Disconnect where? At the alpha beta bond. Why do I keep the minus charge? Where do I keep the plus charge? Obviously on the carbon, that is alpha, so here is your minus minus. This is your beta carbon, keep your plus plus. Now what do you get? Add 2H plus where? Here. Where do I add the O minus? Obviously here. What do I get? Here I will get CHO. What do I get over here? That is CH3. Alright. Now if you do the intermolecular aldol condensation reaction, what will you say? So obviously I will take, if I give you the dilute NaOH, here the OH minus, you will say, sir, I will take away the proton from here, okay, and that will give me the carbon ion. Also keeping in mind that ketones are less reactive. This portion is your ketone, this is your aldehyde, so carbon ion I will not make. Here some amount of product do form. I'm not saying that it doesn't form, it can form. But the major product would be where the enolate will be this one, okay, that will undergo resonance. Okay, that mechanism I think you already know. Then you have, so subsequently that will come back and you attack with the enolate bond, okay, which now gives you something like this, and you have your OH which is in the beta position, so it is called beta hydroxyketone, and under heating conditions, okay, following E1CB mechanism. I'm not going into those details now, I will explain later on. This will go away, that will go out, and you have your intramolecular aldol product. Okay, so now you can see that without using any other technique but just understanding disconnection approach a little logically and breaking the bonds in the correct position, you can come to your starting materials, and those starting materials, with the help of the knowledge of previous reactions that I have already covered in the first year of your BSc and your second year of BSc, by the time you go to the third year of BSc, right, disconnection approach is something that you'll be using a lot more. So now you can see, using those reactions you can actually achieve your target material. By then you have already had the knowledge of mechanisms, how to do things, okay, which is more reactive, aldehyde or ketone, where to make the carbon ion. So these things are already known to you by then. You're making an application of all the reactions you've already studied before. So this is your methods to do disconnection of alpha beta unsaturated aldehydes and ketones. Can be extended to other compounds? Let's see. So here I'm going to discuss disconnection of (1, 3) dicarbonyls, or it is better to say beta keto esters. All right, that is what we're going to do right now. So suppose I have given you something like this. All right. Now, from where do you do the numbering? Let's see. I will do it from here. I'll call this as 1 carbon position. This is 2 carbon position. That is 3. And all I'm going to ask you, again as a rule, you remember, we have to disconnect at the 2, 3 position. Okay? So if you do that, that is your sign for disconnection approach. All right? And then I will say over here at the 3 carbon you put a plus charge, okay, and at the 2nd carbon you put a minus charge. I will say, sir, this is getting a little ready, you know. How do I keep remembering things like that? So if you just use your logic, you will say, sir, this charge can be delocalized over here like this. Okay, that is how I am approaching towards my synthons. Okay. Even in the case of alpha beta unsaturated aldehydes and ketones, if you see at my synthons, the negative charge can be delocalized over the carbon. So here also. Now, whenever you have a negative charge, what did I say? Add protons. Okay. So here you will be adding 1 proton because the requirement is 1 negative charge. So it needs 1 proton to neutralize the synthon, and that is your reagent. Okay. That is your ethyl acetate, isn't it? Now here there are 2 possibilities. You can add OET minus, isn't it? Or you can have another possibility, which is to keep a Cl. So this is your ester and this is your acid chloride. And you already know that your acid chlorides are much more reactive, so it will be leading to a faster reaction. Okay, these are much more reactive than the esters, so leading to faster reaction. So obviously, now if you want to go back to this molecule, what you will think is intermolecular Claisen condensation reaction. That is when you have a long chain. All right. Can I apply it to cyclic beta ketoesters? Let's see. So whenever you have a beta ketoester, all you got to think is the application of a Claisen condensation reaction. It can be intermolecular or it can be intramolecular. Keep in mind, intramolecular Claisen condensation reaction are also known as Dickmann condensation reactions. Okay, that is what it is. Again, same thing. Okay, now here I will mark here 1, 2 and 3. Okay, because I don't want to break the cycle, or rather I want to break the cycle. Sorry. So I will start again from the ester. 1, 2, 3. And again, as the rule was, whenever there is a beta ketoester, break at the 2,3 bond. Okay, so I will break at the 2,3 bond, as simple as that. Now again, what will I think? This is my arrow for the disconnection. Here is my positive charge. There is my negative charge. Keep the logic in mind that I told you before. I need the negative charge to be delocalized. So wherever there is a negative charge, I will add there a proton, and wherever there is a positive charge, I have the option to add OET minus or a Cl minus. So what do I get? Sorry. Okay, let me just flatten this out. This is what will I get. Okay. If you want to be sure about the counting of the carbon, all you got to do 2, 3, 4, 5, 6, and 7. Just check out. Is it 1, 2, 3, 4, 5, 6, 7? Okay, so your answer is correct. Always do the numbering, otherwise sometimes you might end up shortening the starting material by 1 carbon, which is a common mistake that occurs or people do in an examination hall because they want to go to the answer correctly. Okay, so this is the approach that you can use for making or finding out the starting materials of beta ketoesters. Okay, I think I will stop here. Okay, I can still go ahead with the 1, 2, or I can go ahead with the 1, 5 dicarbonyl compounds. Maybe something I will do in the next video. Okay, for now, stay well. Okay, good night.